This video is about how to analyze resistors in parallel. This circuit shows resistors in parallel. We can tell they're in parallel because if we visualize an imaginary positive charge, it moves away from the positive terminal of this battery, follows the wires, which are ideal and have no resistance. This charge reaches a junction where it has a choice. It can travel through resistor 1, R1 here, and then return to the battery, or at that junction, it can travel along a different wire, going through resistor 2 and back to the battery. That choice makes these two resistors parallel resistors. The first thing that we're going to take a look at in analyzing this circuit is the current law. The current law states that the current flowing into a junction has to equal the amount of current flowing out. You can pick any point along the wire and consider it to be a junction, but this is only really interesting at places where the wire branches. This circuit has a couple of those. Before going any farther with the equation, I'm going to go ahead and think about the current flowing through this circuit. Again, we imagine imaginary positive charges flowing away from the positive terminal of the battery, and so that's going to produce a current here. I'm going to go ahead and call that current I0. At this first junction, the current has a choice. It can flow through resistor 1. We'll call that current I1. Or it can continue straight down and around the loop so that it flows through resistor 2. I'll call that current I2. After reaching the second junction on the left-hand side of the circuit here, the currents I1 and I2 can flow back together, and we can call this current I3. To apply the current law equation, I'm first going to think about that junction on the right side, where the current in is equal to I0 and the current out of that junction is equal to the sum of I1 and I2. Looking at the junction on the left side of the circuit, the currents flowing into that junction are I1 and I2, so I'm going to add those together. And those are equal to the current flowing out, which is I3. The sum of I1 and I2 equals I3, but the sum of I1 and I2 also equals I0. So this is just a way of confirming what you may have already realized, that current I0 is the same thing as current I3. Continuing my analysis, I can use Ohm's law to write each of the currents in terms of potential difference or voltage drop and resistance. So according to Ohm's law, current 1 through resistor 1 is equal to the voltage drop in resistor 1 divided by the resistance of resistor 1. In the same way, the current through resistor 2, I2, equals the voltage drop across resistor 2, that's V2, divided by the resistance of resistor 2. We can also tackle the left-hand side of this equation, I0, and talk about the overall potential difference of the circuit, that's equal to the EMF of the battery, and the overall resistance or equivalent resistance of the circuit. So the EMF of the battery divided by the equivalent resistance of the circuit is equal to the voltage drop across R1, but that's also the EMF of the battery, because if we look at these two junctions and how they connect to the battery, that is, the EMF is the voltage drop across R1. So we can rewrite V1 as the EMF of the battery, and we can actually do the same thing with V2. Divide both sides of the equation by the EMF, and you can find the equation for the equivalent resistance of two resistors in parallel. The equation for the equivalent resistance is an inverse equation. So 1 over the equivalent resistance equals the sum of the inverses of the resistors. So 1 over R1 plus 1 over R2. There's a lot of information in this simple equation that we just analyzed. So let's do a summary. We know the overall current in the circuit, I0. The overall current equals the battery EMF divided by the equivalent resistance. We also know the current through each of the resistors. In each case, it'll be the EMF of the battery divided by the resistance of the resistor. And finally, we know the voltage drop across each of the resistors. In this circuit, the voltage drop across each of the resistors is equal to the EMF of the battery because there are plain wires connecting the positive terminal of the battery to one side of each of the resistors and the negative terminal of the battery to the other side of each of the resistors. In more complex circuits, the equations describing the resistance and potential differences will be more complicated. But this example, this analysis, is a good place to get started. That's the end of this video.